All right, let's talk about one of the most important but kind of invisible forces that keeps the internet running smoothly for all of us. It's called rate limiting, and it's basically the digital gatekeeper you've run into 100 times without even knowing it.
I mean, you've totally been there, right? You're trying to log in, you mess up your password a few times, and bam! Too many attempts, try again in 15 minutes. You might think it's a bug, but it's actually a feature. And that right there, that's our first peek into the world of rate limiting.
So let's actually dig into what this thing is. Honestly, the best way to think about a rate limiter is to picture a bouncer at a super popular nightclub. Its job is to stand at the door of a website or an app and control the crowd, just to make sure things don't get totally out of control inside. Okay, so for the official definition, rate limiting is a technique that systems use to control how many requests a user, or any client really, can make in a specific amount of time. The main goal? To stop any one person from hogging all the resources, which keeps the system from crashing and makes sure everybody gets a fair shot at using it.
But it's not just about preventing slowdowns. Oh no. Rate limiting is actually a critical frontline defense mechanism, and it has some incredibly important jobs. Let's take a look at where you see this stuff in action every single day.
First up, APIs. Think of APIs as the waiters in a restaurant, taking orders from your app to the kitchen, which is the server. Rate limiting makes sure that no single app can just bombard the kitchen with 1 million orders at once. It prevents abuse and keeps things running smoothly for everyone else.
Now this one is huge. Rate limiting is a massive shield against what are called denial of service, or DOS attacks. This is when a bad actor just tries to flood a server with so much junk traffic that it literally can't keep up and just crashes. By putting a cap on requests from any one source, rate limiters can stop these attacks dead in their tracks. Imagine you're on a big online shopping site. If one person, or more likely a bot, starts spamming the search bar with thousands of queries a second, the whole site could grind to a halt for everybody. Rate limiting steps in and says, whoa there, you can only make so many queries, ensuring a smooth shopping experience for actual humans.
And here we are, full circle, back to our first example. When a hacker wants to get into your account, they'll often use a brute force attack. It's just a script that tries thousands of password combinations in seconds. But by limiting login attempts to, say, 5 per minute, that kind of attack becomes completely useless.
So, how does our digital bouncer actually decide who gets in and who has to wait? Well, there are a few different strategies for managing this crowd, and each one comes with its own pros and cons. The most common way to do it is by checking the IP address. It's super simple. The system just says, okay, this IP address, 123.45.67.89, can only send us 10 requests every minute. It's straightforward and pretty effective against really basic attacks.
But, and there's always a but,
this simplicity comes with a cost. While it's easy to set up, it's also easy to get around. A smart attacker can just use a VPN to hop between different IP addresses. And on the flip side, you could accidentally block an entire office building or a university dorm, since everyone there might be sharing the same public IP address. Not good. Another way to do it is to limit the total number of requests going to a specific server. For instance, a big streaming service might say, each server in our fleet can handle 100 requests per second, and that's it. This is all about making sure no single machine gets totally swamped during a huge traffic spike.
This is fantastic for protecting the health of your individual servers and making sure resources are used fairly. But a really sophisticated attacker could just spread out their requests across hundreds of different servers, essentially flying under the radar of each individual server's limit.
Okay, this next one is a little different. Instead of just looking at who's making the request, it looks at where they're coming from. By blocking or limiting traffic based on geography, a system can beef up its security or even comply with different regional laws.
This is where you really see that cat and mouse game in cybersecurity. If a company sees a ton of bot traffic coming from a specific country, they can just throttle all requests from that entire region. But just like with the IP check, a determined attacker can just use a VPN to make it look like they're somewhere else entirely.
All right, so we've seen the high-level strategies. Now let's get a little bit more technical for a second. Let's peek under the hood and look at the actual algorithms that power these decisions and enforce the rules in real time. One of the most popular algorithms is called the token bucket. So, imagine you have a bucket. The system keeps adding tokens into your bucket at a steady pace, like 1 token every second. Every request you want to make costs 1 token. If your bucket is empty, sorry, you have to wait for more tokens. What's cool about this is that if you don't make requests for a while, your tokens build up, allowing you to have a short burst of activity later.
A similar but different idea is the leaky bucket. In this model, all incoming requests get dumped into the bucket, but they can only be processed as they leak out of a small hole at the bottom at a perfectly fixed rate. So unlike the token bucket, this one is all about smoothing out traffic bursts and enforcing a super consistent, steady flow, kind of like water going through a funnel. So if you put these algorithms side by side, the real difference is how they handle sudden bursts of traffic. The token bucket is flexible. It allows bursts, which is great for things where a user might need to do a few quick actions in a row. The leaky bucket, on the other hand, smooths everything out, which is perfect for services that need a predictable, constant stream, like video delivery. Then you have others, like sliding window log, which are incredibly precise, but that precision costs a lot more in terms of complexity to build.
So as you can probably tell by now, putting rate limiting in place isn't as simple as just flipping a switch and calling it a day. It's actually a super delicate balancing act, and it comes with some serious real-world trade-offs.
One of the first big questions is, where do you actually enforce these rules? I mean, you could try to do it on the client side, like inside the user's app, but that's a terrible idea from a security standpoint, because anyone could just tamper with it. That's why pretty much all serious rate limiting is done on the server side, where it's all centrally controlled and you can actually trust it.
And even when you get the design right, engineers are constantly wrestling with these challenges. If you set your limits too loose, you're open to attack. But if you set them too tight, you slow down the experience for real users, or even worse, you start blocking them by mistake. We call those false positives. Finding that perfect setting is a never-ending, really tricky process.
And really, that's the absolute heart of the issue right there. The entire goal of any rate-limiting system is to find that perfect sweet spot, protecting the system from getting hammered without destroying the user experience for the people who are using it correctly. It's a constant, ongoing negotiation between security and usability. Which leaves us with one final thought to chew on. In this crazy world of complex traffic and attackers who are always getting smarter, building the perfect defense is a massive, massive challenge. So if you're the one building the system, how do you decide what's fair, what's secure? Where do you draw the line?